Hey everybody, welcome back. So I left the last video in with a bit of a cliffhanger. I posed the question to us of figuring out what the best solution was to this system AX equals 110 when we know that we have infinitely many solutions to that system. Right, so what did it mean to have the best solution? And I proposed that it wasn't just from Gaussian elimination that got us this solution that was possibly the best solution because it was the simplest one and didn't involve using null space vectors that I get from Gaussian elimination. No, I proposed that instead maybe we should look for the lengths of these x vectors to be minimized. Right, we went through a whole exploration to say, hey, there is a solution that has a minimum length to it. And somehow, some way, I got the following solution. That this 1/14 of 1 by 1 by 8 by 2 was in some sense the best or smallest length solution to that system. And it stands to reason, well, this guy did get a smaller number, right? There is a smaller length, and we said that was approximately 5976-ish. So this is the best solution that we've gotten so far, but we'd like to know, is there a better one? Or if this is the best one, how can we show it? Well, let's find out. So remember, for any rectangular matrix with real entries, we have this relationship through the orthogonality of our system, of our matrix, right? We proved that the kernel was the orthogonal complement of the co-image of the matrix, and we also showed that the co-kernel of the matrix was the orthogonal complement of the image of the matrix. And in particular, we're going to play with this relation this time. So the Fredholm alternative played with the image and the co-kernel, and our minimum length solutions are now going to play with the other relationship between the kernel and the co-image, right? And due to this orthogonality between the two subspaces, every vector in R4 can be broken down, right? Because we have our theorem saying that a solution or that a vector can be broken down into something that belongs to some subspace and its orthogonal complement, right? And we can do this uniquely. Every vector can be broken down based on an orthogonal projection and the remaining leg of that triangle, right? So in particular, we know that this z vector we can get as the projection of our vector x onto the kernel, and our w vector is going to be the projection against, say, the other wall or against the other subspace, the co-image. Right, so we know exactly what these two vectors are. Projections, orthogonal projections, are unique, hence why we can turn them into kind of a function. But the point is that if I were to break down my vector x into these two vectors w and z, then notice what happens when I go back to the original system of ax equals b. Well, x is equal to w plus z, and I can split this multiplication, or I distribute the a across the sum. And because z belongs to the kernel, right? Z is in the kernel of a, this turns into the zero vector, which means that b really is just this guy right here. It's just a times w for the appropriate vector in the co-image. And this is the idea that we're going to hammer home here. There is but the one solution from the co-image. There is a solution, and it's in the co-image. And we are going to try to minimize our solutions and show that this w produces the smallest length solution possible, right? And in order to get there, there's a little bit of theoretical work, but it's totally going to be worth it, I promise. So let's take a look at this map where we take an element of the co-image and map it to the image of A just by multiplication, right? So we're just going to say take an element of the co-image and map it into the image of A. My claim is that this is a one-to-one map. In other words, if A of x and A of y are the same here, then the two vectors x and y are actually the same. So this is the opposite of saying that something is a function, where if you take the same element and map it forward, there can only be one location that it goes to in the target space. This is the exact opposite, saying that if you have something that you know is in the image, then there is only one thing that could have mapped to it. So that's what it means to be one-to-one. Another way of saying that is injective. Okay, and I'll leave this definition in red so you can follow along as we go through the proof, which is, again, mercifully short. But specifically, what we're getting here is on the previous page, that the only vector that could have mapped to B is this vector W, right? And this is what we want. It's going to give us a nice uniqueness theorem, or a uniqueness statement. So what we're going to do, we're going to go ahead and assume that two elements map to the same thing. So W and W tilde are going to map to the same vector in this case V, or B, excuse me. Okay, so that's what we're doing here. A W, not the root beer, there we go, and a tilde, W tilde, get me the same vector. So if I take their difference, I can go ahead and say this is AW minus AW tilde, and this is B minus B, so it has to be the zero vector. I'm going to take that left-hand side and factor it, or factor out the A, and that's exactly this statement here that says that W minus W tilde has to map to the zero vector. But when I do that, that means that W minus W tilde has to belong to the kernel of A. But that would mean that I belong to the co-image, because the co-image is a subspace, right? I'm closed under addition and subtraction of vectors. So I'm in one subspace, and I'm also in its orthogonal complement. Co-image of A, orthogonal complement. The only vector that lives in one subspace and the orthogonal complement at the same time is the zero vector. So that means that W minus W tilde has to be the zero vector. And that's this last statement down here, right? We get this nice notion that that our co-image is mapped in a one-to-one fashion onto the image. All right, so we showed that if these guys started in the same one, so AW equals AW tilde, not vector, then that would imply that W minus W tilde is the zero vector, which means that W and W tilde are the same vector. Okay, so indeed, this is a one-to-one mapping. Excellent. Great. What am I going to do with it? Well, we're going to go one step further, right, one small step further. So there is only one vector that can map to B, and that's this whole point, right? There's only one W vector that maps to V. Now, notice, remember our fundamental theorem of algebra, linear algebra, excuse me, says that the rank of A is equal to the rank of A transpose. So in other words, the dimensions here, dimension of the image of A is actually equal to the dimension of the co-image of A. Okay, so we have this this equivalence, or we have we have the same dimension in the space, right? So the image and the co-image, oh sorry, not co-image of A transpose, that'd be the co-image of A. That these two subspaces don't necessarily belong to the same Euclidean space, but they are the same dimension. They have the same dimension, and there is a one-to-one map in between them, which means there is only one element that maps to the kernel, So that would mean that the kernel of this transformation, right, this multiplication by A, is 1 to 1. So that means that we have the same dimension and there is a zero kernel or a trivial kernel for this map, which means that that our bases have to map to one another. So a basis of image of A has to map directly onto a basis for the co-image of A. And that's just via this multiplication, right? And now the real trick. So we've shown that these, so the thing that I really want to hammer home here, if we go a little bit further into the theory, is to say that these two spaces are actually isomorphisms as vector spaces. They're isomorphic as vector spaces, right? So they behave identically from a linear algebra standpoint. But we won't go too far there. Time to show you some magic. And the theorem that we want here is that for any element B, any vector that lives in the image, right, something where we do get a solution to AX equals B, there is but a unique solution, but one solution that lives in the co-image and still solves this system. So I would be satisfying two conditions here. That I have something that solves AX equals B and that it lives in the co-image. Okay, and this is what we're going to use. We're going to wind up invoking some orthogonality here to make this vector as small as possible. So this vector W does indeed have the smallest length among all solutions X of the system AX equals B. So specifically, if I have two solutions, W and X, of that system, then the length of W is always going to be smaller than the length of X. And I'm saying this length specifically in terms of the standard Euclidean distance, so the standard Euclidean norm. So this is the 2 norm for those of us who are being very pedantic, and you should be. Should be very, very skeptical whenever I use a norm, but don't actually say which norm it is. But because we're working with orthogonality, right, we have to be sitting in sitting in an inner product space. And the only time that I get an inner product space for the only time I get an inner product here for a norm is when I'm dealing with something that comes from an inner product. So I need to make sure that this is the norm induced by an inner product, and all the work that we're doing with the 4 fundamental subspaces is with the standard dot product on Rn and Rm respectively. So this is the 2 norm. All right, our general solution then. We know this from chapter 2, right? There is a general solution to the system that can be broken up in terms of some particular solution and something that's offset by the kernel. Right, and specifically because we're in chapter 4 here, because we're dealing with orthogonality, we can split up X into 2 pieces based on the orthogonal projection of X onto its kernel and then onto its co-image. So W would have to live in the co-image. Right, so here's the deal. If we were to compute the length of this vector X, well, X is equal to W plus Z, and this length squared, remember I'm going to invoke bilinearity of the inner product, so this is W plus Z, closed out a little too soon, W plus Z. So I'm going to wind up with an inner product of W with W, W with Z, Z with W, and Z with Z. Okay. The first and last entries here, W with W gets me to the norm W squared. Z with Z gets me to the norm of Z squared. Great. But what happens here? I invoke symmetry to get me both inner products, or I get the same inner product. So I'm just choosing W dot Z here. But we know that the kernel and the co-image are orthogonal subspaces to one another. And this is what this little black arrow is saying. is that because these two subspaces are orthogonal to one another, this guy, w.z, vanishes. Right? The dot product between any element of the kernel and any element of the co-image must be 0. Which means I can ditch this inner product in the first place, or this middle term, the mixed wz terms, and what I wind up with is something that looks like w squared plus something that is no smaller than 0, which means if I add any non-zero vector, if I add something, some non-trivial z vector, then I get a norm for x squared that is strictly larger than the norm of w squared. And I'm done. It means that if I add anything outside of the co-image, then I am going to be lengthening the vector, which means I have to be completely contained inside the orthogonal complement of the kernel, which is the co-image. And we've already shown that there's only one vector that can solve this system, and that's the w. Awesome. So coming back to the original question, how did I find this? Well, not only am I row reducing this system, this guy, A augmented with B, right? If I go back to MATLAB here from last time, remember A, reconnect because the session expired. Yeah. If I come back to MATLAB, oh, come on, don't freeze on me. Don't halt. No. Let's see if we can't fix that. Oh, come on, shrink. There we go. Kill that off, go back to OneNote, and then try to reopen MATLAB. Connecting to MathWorks Cloud. Connect a little faster, thank you. There we go. So here's A, it should remember, yep, A, B, right? So if I were to row reduce the following system, A augmented with B, this is exactly how I got the 4, 1, 0, 0 from last time. I need 4 of the first vector, 4 of the first column, 4 of the first column, 1 of the second, 0 of the third, and 0 of the fourth to create this solution vector. And we made this guy equal to, I think, oh shoot, I don't know if we actually named him. Yeah, we did. Big X. There he is. Yeah, X is equal to 4, 1, 0, 0. So that is still a rank deficient system, right? I still have 2 degrees of freedom, right? These free columns in row 3 and 4 of A augment B that I need to fill in. And what we're going to do here, in order to pin down this solution, oh shoot, killed it, uh-oh. In order to pin down this particular solution, the one that lives in the co-image, we are going to have to make sure that we include conditions that force us into that space. Those are the orthogonality conditions that I'm talking about down here. That I need to make sure that if I have a basis for my kernel, my co-kernel specifically, then I have to add those guys into, I have to add these orthogonality relations into my solution, right? This X solution up here needs to be orthogonal to everything in the kernel. So let me do that. If I go back to MATLAB, I ask what the kernel is. The kernel of A was this matrix. So I just need to go ahead and add into the bottom here. So I will be creating this new A matrix. And new A is going to be the previous setup, right, where I have the augmented A by B system, but I'm going to go ahead and add in the bottom, a null. Oh shoot, I should probably name this guy. Yeah, so let's do N for null. N equals null of A. Great. So I need to make sure that I'm perpendicular to the kernel. Yes, so I would need to create this matrix new A, which is A augmented with B. And then I'm going to ask for N, I'm going to ask for the first column, and I'm going to transpose it and augment against the 0. So this means that my solution has to be perpendicular to that first column. And for the second part, I'm going to put in the second column, and that has to be perpendicular, or almost my solution has to be perpendicular to that vector as well. So notice that that's what it gives me. And what I would like to do here is compute the row echelon form of this matrix. Drum roll, please. There we go. That looks awfully familiar on the right-hand side. Right, if I ask for, let's see, proposed x rather than prop x, let's say that this is new, that'd be the first 4 rows of the last column. What? Oh, new A, not new. There we go, new A. There it is. Indeed, proposed x here. Did I do that right? 1 to 4 of the 5th column. Oh, no, that's shame on me. I have to go back. Reduce row echelon form of new A, and I have to ask of the answer proposed x is equal to answer 1st to 4th rows of the 5th column. And there we go. This guy should look familiar. Norm of this proposed x is about 0.5976. And if I multiply this guy by 14, that's 1182. This is exactly the vector that I needed. This is the one that lives in the co-image of A. And this, because it lives in the co-image, is the smallest length vector that I could possibly create as a solution to this system of AX equals B. All right. Let's see, last page here. So yeah, you can go ahead and show that these are the conditions. Yeah, this is what you would do if you were doing this by hand. Right, I highly recommend doing this with a computer. It's really not too much extra work, but you should know how to do this by hand, especially if I ask you to reproduce this kind of result on an exam. All right, but otherwise, that's the end of this chapter. Right, we are done with chapter 4, and we will be moving on into chapter 5, talking about kind of expanding on these ideas of minimizing solution lengths, or finding solutions that are, you know, closest to the correct location, but not quite there. And we'll develop these ideas next time. I'll see you in the next chapter and the next video.